So today we're going to look at breaker monitoring and waveform analysis, and the big emphasis will be on the waveform analysis. We currently have a monitor on the market that very closely emulates first trip type testing. Several companies provide those test sets. And I thought I've had a lot of customer requests to go over, well, what are we looking for when we do these waveform captures? What are the, what are the type things we need to be concerned about? What's unusual? So we're going to look at some of these that I've captured both with handheld test sets when I was with the utility, as well as some from our online monitoring, and just kind of discuss what we're finding. So kind of a little preface to this. I work for a municipal for, actually I worked there for close to 28 years. And I found, so we were by large a distribution utility. We bought all our power from TVA. So a lot of distribution breakers. Our high side was 161. A lot of the equipment we had was 23 or 12. And I found that our CD and SAIDI times were really increasing rapidly. The last few years I was at the company, and when we got to looking into it, we found that a lot of that was due to breaker misoperations. So essentially, we were an offline test only type of company, just traditional timing and travel tests, ductor type test. And that was what we were doing to try our breakers. And we tested on about a 5-year cyclic maintenance with those. So around 3 or 4 years before I left, and I saw these outage numbers starting to go out, we were seeing a lot of breaker fails on our distribution side. And they were breakers that I actually had pretty good tests for. So I thought, well, we need to come up with another way to do this. And I was introduced via a friend to the first trip testing. And we started going into that and finding that we had a lot of these breakers that I was getting good timing from timing and travel tests that were very, very slow on that initial operation. So, my takeaway was that not only is that putting a lot of strain and causing increase in outage times, but the effects it has on your transformers too. If you start going through and looking at the stations historically where we knew we had these slow operation problems, you would find those were also where you had transformer problems a lot of the time. So there's definitely a correlation through those, between those, and we'll go over that. And a lot of we had several failures that were just due to breakers that did not operate. Now that can be related some to your relay scheme. I mean, the 2 instances I'm thinking of, there were no breaker fails in place. Kind of remote stations, fault currents just didn't make it back to kill the line at the station before, and something as simple as something getting on that bus and that high side not being able to come open. We saw 6 minutes of through fault on one of the events, failed the low side breaker. The fault was believed to happen somewhere between the low side breaker and the transformer. Low side breaker couldn't clear it. The high side breaker failed to operate. No breaker fail in place. So 6 minutes resulted in a loss of that entire station. It's 2 transformer station. Sadly, the fault lasted so long, it actually hit the cable tray in the station and burnt the station house up as well. So we were looking at 6 to 8 months of outage over that, just millions of dollars, a lot of line regulators. So, I mean, these breakers, that's really the reliability you have of your substation. Are these working as they should? And I know, especially the company Dynamic Ratings where I work now, we do a lot of transformer monitoring, and it is a very useful product for catching things early and in their inception when you talk about transformer problems. But you also have to remember that that transformer is only as good as the breakers there on either side of it. You're a breaker fail away from really doing some damage to that system. So when we talk about breakers, it's a little different than when we're talking about transformer failures. Transformer failures generally, a burnt winding, something of that type, and it's done, and that's the end of that piece of equipment. When we get into breakers, there's a couple kind of failures that we need to really consider. So major problems. These are breakers that just they don't operate. So you send a command out and it does nothing. There's no interruption. And these are the ones that really get looked at. So when you look at these, you can see from the graph here that somewhere roughly around 75% of these are directly related to mechanical problems. So when we start talking breakers, we're talking a lot of linkage, lubrications, that kind of thing, and that's going to be in large part why we will have these breakers that won't operate. And like I said, these are the ones that I know every time we have one that just a breaker fail occurred, or there was just a failure to operate, oscillography gets pulled, everybody pours over that. We start trying to figure out exactly what went wrong in that instance. Maintenances are scheduled and that type of thing. So when we go to this next failure, and I feel like this is the one that gets missed in large part. I know a lot of my utility and a lot of utilities, if a breaker opens and there's not a breaker fail or anything to draw attention to that, then that operation is really not looked at. It's just assumed that the breaker operated properly. So when we talk about these, we're talking about breakers that operate. So they do what they're supposed to do, but they're not doing it within the time that's allotted. So if you look at a typical scheme, you may have distribution breakers, and then you're going to have a bank breaker between those distribution breakers and the transformer. And generally, you're going to have some type of delay there. So a fault occurs on the line, distribution breaker is supposed to pick that up. The whole system's looking at it at that point, and you may have a 15 cycle delay set between that bank breaker and that distribution breaker. So it's counting. Well, that distribution breaker does not operate. Now we're 15 cycles out from seeing that bank breaker actually interrupt that fault. So that is fault current that transformer is accumulating in that line. And you could have 4 to 6 distribution breakers. You get a couple of bad ones in a fault prone area, and that transformer is seeing a lot of duty that it really should not see. So what's that do to our transformer at that point? Well, this was something I found in T&D a while back, and I really thought this was the best explanation of how that's affecting the transformer. So when the breaker's not operating or is slow to operate, let me rephrase that, is slow to operate, we're seeing a longer duration of fault current. So let's say we have a 3 cycle breaker that's out there, and that's 51 milliseconds that we get to clear that. But you've got to remember, we do have this 15 cycle delay in between those. So, roughly, I'd have to do the math. Roughly, so quite a bit of time longer that fault's in. So let's just say that distribution breaker is, let's say it's 2 cycles slow or 4 cycles slow. And from testing in the field, I found that these slow operations generally are lubrication related, and they tend to worsen over time. I mean, so where you start out with something that's a few milliseconds and it goes to 2 cycles and maybe 10 cycles, but you have to remember, until we hit this 15 cycle point, we're not going to operate the break that bank breaker, and nobody's really aware that that's going on. But the transformer is still seeing all that. So now if we see a 3 cycle breaker, well, we could be exposing that transformer to 10, 12 times the duration of that fault current going through it than what it should be seeing if our protection was working correctly. So when you do that, you place a lot of thermal and mechanical stress on that transformer during that event, as with any fault. But that increased duration of that fault is allowing a lot more thermal degradation to occur to those solid insulation systems. So essentially, you have your core and coil assembly, and then you have that solid insulation on the coils. That is getting burned away the longer this these faults are held in place. And as that happens, we're actually losing mass from what's being clamped. So you have a clamping system on that core and coil assembly that that's the strength of your transformer. It's keeping those radial and axial movement from occurring during these events. Well, as that mass is decreased because we've lost some of our DP of our solid insulation, that clamping force isn't as strong as it was, say, coming out of the factory, which is allowing just a slight bit more movement. And that's why you see a lot of failures that happen where, okay, we had a through fault, but really probably shouldn't have taken a transformer out, was interrupted as it should have been, or what, but we still see that failure on the end of it. And this is something that's really hard to catch. You can do DGA testing, and that gives you a pretty good idea of anything that's happening long term in the transformer. You have partial discharge, or you have something in excess of 250 degrees C or 300 degrees C. So we're starting to see some ethylene development or something like gassing of that type of pattern. The problem with these events is they're so short lived, and without the presence of online monitoring, which I did not have a lot of at the utility, if you only have that sample being pulled once or twice a year, if you don't get out there within a timely manner after the event, a month, 2 months, you're really not going to understand the seriousness of how that heat affected that transformer. Most of because gases tend to migrate pretty quickly into any type of headspace that's available. And of course, that changes. Hydrogen's very fast. Ethylene slower, acetylene slower, but they still do find their way out of the oil over time. And so you really don't understand how that transformer was affected unless you have a 24-hour sampling or monitoring of DGA going on. And then the other tests that we run in our usual maintenance would be power factor testing. And that's really hard to see movement of that type. So because it is a very small grade of movement in the beginning of this problem. I've seen transformers that actually had one that comes to mind right away. I had a low side bushing failure. Went out, we did a power factor test. Everything looked pretty normal. We took the bushing out and we're going to replace it. Decided to do an internal inspection before we went through the trouble change out. Look, all the bracing in the top of the transformer, it was shattered. I mean, the blocking assemblies on the top of this coil, they had moved a good inch out of a line. So that was the effect. Just that short of that bushing to that tank in that close of proximity had caused that much movement of the core and coils. However, the capacitance in the test really had not changed a lot when we were looking at the power factor. So the only way you would really be able to catch this type of event with any kind of accuracy would be SFRA testing is what. So you would have to have a good representation, a representative SFRA initially of that transformer was in good health, and then after these type of events, you would have to run another SFRA, or you would have to make that part of that cyclic testing that we do on transformers to start seeing these changes in their inception. So breaker monitoring and online monitoring of breakers is something that it's been around for a while. It seems like it came around, I don't know, maybe 15, 20 years ago, kind of faded out, and now it's come back in the forefront. And again, we have a product and several other companies do, but this is just kind of some of the things I've seen that for breakers where this would really give us some advantages in not just the health of the breaker, but the health of the equipment that you're looking at. I feel like you really got to consider temperatures are one of the big things to be looked at, and that would include ambient temperature as well as a cabinet temperature and a gas temperature to understand, what when it gets cold in at night and you're calling crews in, you're getting these calls about leaks. Is it a leak or is it a temperature related thing? Are my tank heaters working? Are my cabinet heaters working like they should? Because that results in condensation forming in cabinets. I had a lot of OCB breakers when I was at the utility, and would find that the fuses, the cartridge fuses, they had gotten so wet that they had just disintegrated in the holders. And again, now we have a fail to operate that comes into play. Wire that had become so corroded that it just broke out of a terminal block. So these are why these things are important. And then when we get into talking about online monitoring, it's much like offline testing. It's important that we have something that's capturing that timing. I recommend, it's something I implemented utility, and something I recommend to all of our customers. Really, you have to institute some maintenance tripping of these breakers. You'll have breakers that'll sit there for 10 years and they don't move. And that's really the biggest enemy that you have to these breakers operating when you need them to. So as breakers sit over time, we find that the grease and the bearings are all the grease in a breaker. So grease is made up of two components. You have a thickener, which would be like a clay or a soap, and then you have a lubricant in that thickener. Well, as that sits over time, those tend to separate out. So they're, it no longer mixed up. That lubricant leaches out of that thickener, and we'll find that we have kind of a almost a gum sitting in all our bearings at that point. So that's the reason for this first trip type of thinking, because once you operate that breaker and it's cycled, now you've kind of remixed those components, and that next test is going to look pretty good. And you'll see in some of the examples from the offline testing I have that you can see first trips 400 milliseconds that fall within nameplate after the second trip. So if the only testing you're doing are these offline type timing and travel, which are vital tests and have their place, by no means disparaging that, but you're missing a lot of the data concerning how that breaker is going to operate. Again, when we get into monitoring, you would also need to look at motors. That would be a huge thing to understand how that motor's running, especially when you come to pneumatic hydraulic type systems, to understand, do we have leaks developing in these stored energy systems? Are motors running when they're supposed to on closes for springs? Are we seeing that motor run that's causing a charge? SF6 we're all aware of, and that should be something that everybody should be taking a close look at. I think the online method is really great in that it allows you real-time views of these data. It's like I said, I've had a lot of people call me, and I experienced a lot of utility. I get a call and a breaker's going to alarm. I got an SF6 alarm. Well, I have to call a crew out at that point. So now I'm rolling a truck in the middle of the night, and we go out there and find out that, hey, pressure's right where it should be for the temperature we're at. And then there's also topping off and understanding, and I think I have a graph in this presentation just to understand that when you top off these breakers, especially when you have tank heaters, a combination of tank heaters not working correctly and top offs during cold weather events actually can lead to leaks developing on that breaker when it does get warmer. So these are just kind of the things that I thought, if you're looking for breaker monitoring, this would be the kind of things that you need to think about. These are the things we need to capture to pretty much ensure that the health of that breaker. So a lot of this monitoring and a lot of the online testing, like First Trip, which I mentioned, we go into waveform capture, and that's the idea, is that you set triggers associated with current flow through trips or closed coils, and as soon as that current through those devices exceed a threshold, the monitor will go into a capture. And the basic idea of this is that you do not take this breaker out of service. You want to test it when it hasn't operated for a while. So we're trying to catch what's this going to look like in real life when it has to clear a fault, as opposed to what does it look like after we've just operated. So just to kind of quickly go through this and explain what we're looking at. This is a graph just kind of typically explaining what a trip coil would look like. So if we start on the left of the graph here, starting right here. So relay sends a signal to the breaker. That trip coil is going to start energizing. We will see this line begin to climb. So that plunger is now being pulled through the coil and is traveling to strike the latch. At point B, that plunger has now reached the maximum velocity that it can reach. So we're gonna see that current start to fall at that point until we hit C. Now the C is where you will hit the plunger. This is a really good, or hit the latch, excuse me. And this is a really good reference to understand how that first part of the operation is working. It was something I always looked at. Is this latch point lining up? Especially when you get a slow operator, to understand, okay, am I looking at the plunger movement, the latch, is it not coming off as it should? Because this will move both higher in the current and further to the right in the time scale if you're having issues with that portion. So after we've gone through that latch, we're going to see that velocity is continuing to be at the max. And so we're going to continue to see that current fall until we hit point E, and that is our buffer. So that means that that plunger has traveled as far as it can through that coil and is now stopped, which is going to ramp our current up to point F here. So that should be the max current that we're going to draw from that coil. The plunger's at a hard stop, and then that portion will last until we roll over to G, which is now our 52A contact rolling open, and finally we de-energize back to zero through this coil. Now, just a quick note before I get into this latch point. You don't necessarily always see that when you're testing. I know with a lot of vacuum breakers and various designs, sometimes this latch is not really that noticeable in the signature, and you'll see it in some of the testing that I'm going to show, that this is, it's not always apparent. However, this buffer pointer E is always there, and I really use that as my reference to how well did I move through that initial part of the operation and get to where my main contacts, or the main cam of that breaker, is actually starting to move, allowing that breaker to come open. Also, for proper analysis, and this is something we'll see in some upcoming slide, you do need to have some knowledge of how that mechanism's working. As I said, that the latch is not always going to be apparent in the waveform. Sometimes you might be hitting something that actuates the latch and it's not actually striking the actual latch to pull it. So things like that, to understand what you're looking at is going to help you go a long way towards making an accurate diagnosis of what you're seeing when you do run across a problem. And another thing that's really critical, and it's really one of the advantages you'll get from offline test or online testing, and it could be done in an offline as well, if you're able to bypass and put things on reserve and not to that type of thing, is that the oscillography of the current flow through the main contacts. So if you can get a high-speed capture of that in conjunction with these coil signatures, you're really able to do a pretty accurate, detailed diagnosis of what's going on with this breaker when we do find a problem. And then the ability to overlay these operations. That was the trick when first stress testing, when we were in the field doing first strip tests. You always want to be able to compare. So we'll take that initial operation. The breaker's been sitting static for a long period of time. We'll operate. We get a capture. We'll close. We operate immediately again, and then we want to be able to overlay those. And we're looking for any small changes. Everything healthy breakers, I would expect to see 2 or 3 milliseconds of variance, and really no more than that ever. I mean, usually it's almost a direct overlay from operation to operation. If you're not seeing that, you probably do have some lubrication issues, some type of adjustment issue in that mech that needs to be looked at. But it's important that we capture all of these to be able to compare, trip coil, aux contacts, to the load current and what's it look like to really make an accurate diagnosis. So this was one I captured, and this actually was a vacuum type breaker that I caught when I was working at the utility. And I think this is when we first started initiating this first trip type test. And this is what we were seeing a lot of with our breakers. We had a pretty old fleet. I think our average age of breaker was maybe 42 years, somewhere around that. However, I would find that quite often we would have fairly new breakers that, just weren't operating. And we would see this type of thing. So the red line in this graph was actually the first trip of that breaker. So there, we can see that we ran out around 115 milliseconds with that first trip. And that was the time that really interested me because, again, we're outside of the rating of the breaker. However, we're still inside that breaker fail scheme timing. So this breaker could operate like this for quite some time, and we would never be aware. Nobody would be aware this was happening. So if we go back to the blue line in this operation, and we can see that this breaker, it sped up 100 milliseconds, or close to 100 milliseconds, just from one operation to the next. So again, this is the kind of thing that you really got to start thinking about your transformers. It's just you're sucking the life right out of it if this breaker is sitting there consistently taking this long to get open and clear faults. And another thing that really I have some slides to show that's interesting. Once you start seeing this type of pattern where first trips longer, as time progresses, if it's not addressed, it gets worse over time. So when you do get that breaker fail, keep in mind that could have been slowing down over a period of 2 years. I mean, you don't know. It's such a large window when we're looking at something that happens so fast that there's just no way of knowing. Well, I wonder how much fault time I've accrued on this transformer that I really shouldn't have seen if everything had been working properly. And again, I go back to maintenance trips. And if you can do that with either online monitoring or first trip test set, it's a great idea to get out and exercise these breakers once a year, once every 2 years, and get this done to really understand what kind of condition your system is in. So this was an actual online monitoring lubrication issue that was captured. Just to give you a brief history on this, when this monitor had been in service around 8 or 9 months, and this was what the typical waveform overlay had looked like. So we can see our low current, we can see no latch apparent on this one, but we do see that this buffer is being struck roughly the same point. And we also see this 52A is rolling off at within 1 millisecond of every time this breaker operated. And so going through the data on this went on for 8 or 9 months. However, at some point after that, they had an operation. And another good thing to make note of this was actually at a renewable facility. So this breaker is getting operated once or twice a day, every day, switching between solar and steam generation. So after 8 or 9 months, we start seeing this kind of signature. And for time, I just grabbed a couple of grabs out of it, but we're looking at maybe, sorry about that. Maybe 3-6 milliseconds here is what we're looking at with this one. However, as you looked at it over time, it went from 3 milliseconds to 8 milliseconds to 20 milliseconds to 30 milliseconds. And so over a period of about 4 months, we end up with something that looks a lot like this. And this is where we're starting to see, okay, now we've got a breaker fail that operates. We've also forced a shutdown of that facility at this time. So one of the things I really wanted to show with this to understand and the advantages of having all of them. And so aux contacts on this particular breaker it was a switchgear type setup. Those aux contacts are operated off of another contactor in the breaker. So there's a pickup time with that. They were about 50 milliseconds behind the actual operation of the breaker. So we're really not getting a lot of data from the aux contact change of state for this one, which makes another good case for that's really not where you want to time things. But we can see that this current was, and they were running around, I want to say this was around 400 or 500 amps we were running in normal. But we can see that this breaker starts to open, this current drops to almost zero. So it was dropping very low, around 50 amps, I think, during the initial part of this failure. But then we see that the current is ramping back up at the end of the operation. So now we have to start asking, well, what would cause that type of signature? So one of my thoughts was vacuum bottles. Knowing it was a vacuum breaker, I'm thinking, okay, maybe we've got a vacuum issue going on. But we see that here, when these 52As roll off, current's killed immediately as soon as that happened. So you kind of have to dismiss that idea at that point. And looking at how this current almost goes to zero, and then we see this current, it's about 4 times the normal operating current before it's extinguished. So we're running around, like I said, around 4 amps. We were pulling around 1,200 amps in this portion of the operation. So just looking at this and thinking it through, it's like, well, it really looks like this breaker's not coming. The contacts aren't parting as far as they should part when the operation's initiated. So thinking it through, it seems like, well, seems like it would probably be a latching issue to me. So luckily, after the customer sent me this and I was able to get back to them and say, well, this is what I think. A month later or so, they were able to actually pull this breaker out of service and test it. And they were nice enough to catch a video of it when they did it. So just to give everyone some reference here, what you're looking at, this is a switchgear type breaker. It's racked out. And we're going to see the plunger is going to come down from right here. So relay's going to initiate, coil's going to energize. We're going to see this plunger start to move. However, if you look here, we have a sort of a flap that's attached to a spring. So not actually hitting an actual latch. So that's why we're not seeing the latch in the signature, but it is going to initiate the latching mechanism. We will see, and that will be this arm will start to fall. And then this is our main cam, and this is where our main contacts are attached to. When this first initiates, this moves a little, but then this stalls. And so we're not able to release that stored energy immediately. We sort of let a little pressure off those contacts, and then once that latch clears totally, now we see a full open. So this is slowed down quite a bit, but it still all happens pretty fast. So you have to pay attention. But this just shows the kind of accuracy that you can use your monitoring or testing to predict what's going on in real time. So we can see this latch took a long time coming off, and we see it actually came to a stop right about here, which had, like I said, let this main cam initiate slightly at the beginning, but not enough to get clear. So we've got contacts that are sitting there, and if we go back, we can actually see through here, we have a lot of arc time going on, in this breaker. So again, just a way of looking at the graphs and the captures of all the different currents and diagnosing the type of problem that we're seeing. So this was another graph that was captured, and this was a bad wiring, a wiring issue with the breaker. So this would be another type of waveform that we would look for. The red line being the initial test of that breaker, and the green line being after repairs were made. So we can see this red line. Everything looks pretty similar through the latch portion up to max current portion of this capture. However, once we get into there, we start seeing this erratic signature, this up and down, and then the big telltale of this. And this could be, it could be wiring. It could also be a corroded up auxiliary contact that's sticking a little bit or just not making good contact. But we see this kind of tapers off in the red line. We don't see this nice clean cut of current through the coil like we would expect to see when that 52A comes open. So typically this will happen during that max current portion of the capture when that coil's pulling as much as it can. We'll start seeing these things that relate to these aux contact issues or wiring issues within that control circuit. So just another type of thing that can be seen in this type of testing. So this was another signature that I captured at the utility. And this was an interesting one because we burn up trip coils, which seems to be, we have supervisory and circuits in place. We do some integrity monitoring, that kind of thing. But why is our trip coil failing? So this was a breaker that had a history of failing trip coils. And actually, we did have quite a few that had histories of trip coils. Trip coil replacements were beginning to be a regular thing on some of our breakers. So when we look at this signature, we can see that this coil does energize. We see that we hit our latch right here. We see our buffer gets hit, and we see we go to our max current portion of the waveform. The only problem is we're staying energized around 900 milliseconds with this max current. If we go down here and look at our main contacts, we can see this breaker really opened up somewhere around 40 milliseconds, somewhere in that neighborhood was where the contacts actually came open. And so when you see this type of event, that auxiliary contact is staying shut. And again, with more operations, you'll see this start to change. It may get better apparently after you operate a few times, but if it's really something you have to go in and do some maintenance on this, because the coils are not designed for this sustained current for this amount of time. So as this breaker operates, within 10 or 12 operations, now you're going to be putting a trip coil in it. Again, that's after we have a breaker fail though. And really without this type of testing, there's really no way to see this type of event, which again, just lends itself to, we really need to step up those maintenance trips and that maintenance as much as we can. So this was an interesting one in that this is actually a DC voltage trace we're looking at on the top, and we see all of this AC ripple that's being introduced to this. So especially as this breaker is really slow on this first shot, so we're pulling that current for a long period of time. And I saw this a lot as well when I actually had some old solenoid type mechanisms. So rather than drawing 6 amps, 12 amps, I was seeing more like 40 or 50 amps in an operation. And you start really understanding the health of your batteries when you see that kind of load being thrown on during operation. But this is a good sign that your battery charger is probably not being filtered out properly. So we're starting to see a lot of AC bleed coming over the system. Another thing that we would look for in a prolonged operation is this starting to dip. Would be the next thing that we would start seeing. So this current would come out and we would see it actually dipping down during this operation. And again, without this capture, you really, it's hard to see with just a regular monitoring of your battery system to see this type of event, because it does happen so quickly most of the time that without this type of capture, you're just not going to make the association. So this is another useful point of these first trip type testing, and another thing we can collect from this waveform data. So this was another one that came off the monitor, and this was actually a closed coil, and this was another problem that it sort of self-corrected initially. So if we look at the left, when this breaker, and it had not been operated around, on that first close, we're seeing that closed coil staying energized about 3 times longer than what it was on the second operation of that breaker. Don't pay any attention to amps, guys. That's just where the cursor's at. I'm sorry, I just now noticed that. But we're looking at the waveform. So again, when we talk about auxiliary contacts, we see this same type of signature happening, where we see this sort of sloped off de-energization of the coil. And then when the breaker was operated for a second time, we see that that's kind of cleaned itself up. But that's not to say that the next time, if it sits for a while, that these don't just sit just completely shut the next time, or it takes 20 times as long. So this is the beginning of the problem, and really we need to get in there and start doing some maintenance at this point. I mean, the whole idea of the testing or online monitoring of it is we want to catch these failures before they happen. And so these are the types of things that these tests will tell us that, okay, if we go in and address this now, we can have a planned outage on this equipment. We're not seeing lost time because of it as far as service time to customers, and we're able to keep our whole system up and running much more efficiently. So this was another slide that was captured from data from an online monitor. And I wanted to show this. It's not a waveform capture per se by testing, but just we were talking about SF6 and how temperature affects these, and the things we can see when we start plotting out these various values. So the orange line being a temperature, ambient temperature, is what we're seeing with it, and the blue line being our SF6 pressure. So we can see that we're running around 87, 88 pounds of gas on this breaker, which was slightly above the nominal pressure for it, probably due to some top offs at some point. So, and this was at a warmer time, but we can see as we go through, when we start seeing these sub negative 10 degree drops in temperature, we usually just follow directly by about a 7 or 8 PSI drop in our gas pressure on almost all of these big drops. We're seeing this peak come down. So not a huge deal, however, because the breaker was pressurized to the point it was. But if, let's say it had been at 80, which is not that uncommon, these would have all went into alarm. We would have seen alarm points at all of these, at which point we would have went out. We would have topped this breaker off. But the big thing that we notice here in this graph is we're seeing these drops during these times, and they did have tank heaters on this breaker, and really we shouldn't be seeing that. So the monitor did provide alarms that, hey, we've got tank heaters, they're not working. They go out and check it, and they were not working. Actually, on this job, I think they forgot, the contractor that installed these never took the RTDs for the tank heaters out of the ambient temperature out of the cabinet. So we got RTDs sitting in the cabinet that's heated by cabinet heaters, and it never knows that's that cold out, and thus the not working. What really interested me about it was that once the tank heaters were repaired, to see how much the pressure actually increased with the tank heaters working. So if we look, this is in February, really cold, subject to be running a little low on pressure anyway. We're seeing 10 pounds, 11 pounds of pressure increase every time that tank heater cuts on. So this kind of makes it a case for this alarm. So when we get these alarms, these cold weather events, with density monitor, we don't know when we get the call. We have to go out there and look. And the key is we got to get it out of alarm. But you need to understand, especially when tank heaters are involved, if we top this off and we do it up to a higher pressure, so say 82 is nominal, we go up to 86. Now we are putting 96 when the tank heaters come on. Now, if suppose our thermostat goes bad and tank heaters stay on, well, now in the summertime, we're going to blow a rupture disc on this breaker, or we're at least going to put enough pressure on the internals of those tanks that we're going to stress the gaskets, all the joints, to the point that now we've created a leak issue later on, when that breaker's in service, and that's going to be something that's going to be, we're always going to be addressing. So it's just something to understand the correlations between the temperature, the gas pressure, the heaters, and how all that works, and how, without looking at all this data in real time, it's really kind of hard to get a good picture of what's actually happening with that equipment. Are we really in good shape, or have we got something that's kind of starting to sneak up on us, and it's a problem? It's going to be a problem that's going to get us eventually, if not addressed. And that was what I had for today. Thanks for having me again, Randy. I do appreciate it. I'm happy to take any questions if you have them.
Yeah, Chris, thanks very much for the presentation. Before we get to the questions, I just wanted to mention to you that I don't have the presentation from you for today's presentation. I have the circuit breaker presentation from before. So if you could drop that, if you have the PDF there, if you could drop that in the chat, then everyone will get your presentation from today. All right.
Yeah, no problem, Randy. I'll have to
and
find it here real quick.
The first question is, what are the common failures of the SF6 circuit breakers?
Obviously, your most common is going to be gas problems. I mean, with modern SF6 breakers, that's by and large what we're going to see more than anything. Leaks, lockouts, cold temperature lockout are going to be first and foremost of our problems. I'd say the thing I've seen, the second most common problem, are these slow mechs. Again, especially when you get into like a transmission type situation. I had breakers that had not operated in 12 years. I mean, they had been just sitting there stagnant, and then when they need to operate, they don't. And that's simply a lubrication issue at that point, most of the time. I mean, it's pretty much just gum shut.
Okay. Like I asked Fouad, and I don't know if you were online during his presentation, I asked him, he mentioned that 40 to 50% of all transformer failures were tap changer caused failures. And I asked him what percentage of those transformer failures were young and old transformers. Are the failures across the spectrum of age, or are they isolated to the majority of transformer failures isolated to older transformers?
So I assume you're asking about breakers in that case, Randy.
Yeah.
So I would say definitely with the newer circuit breakers, we have less moving part, fewer moving parts, less lubrication points. Definitely a much more robust and finicky product than, say, if we go back to OCBs.
Right.
That it's been a lot of great improvements. However, that being said, I have come across some new ones that fail out of the gate too. I mean, so it's kind of hard to say. I would say more than age is a factor, and definitely you see more failures with the older stuff than you do the new stuff. But more than age, I would think one of the largest factors is how long is it sitting and not moving. That's really what's going to make a difference. Is it going to work when I need it, or has it been sitting out there for 10 years and nobody's done anything to it, and now we need it all of a sudden and it just doesn't work?
Yeah, have they when they redesign breakers, have they redesigned them in a way to make them more reliable?
Yeah, I think the newer stuff is definitely the reliable. Like I said, I think we went from, oh gosh, I don't know, 30 something loop points on the old one. I think a lot of the newer breakers, you're looking at 7, and some of them are none. I mean, it's just they have greatly compacted and simplified the moving parts that are involved. And when you start looking, if you take an OCB, I mean, that's 12 inches of throw where those contacts are separating every time to get that arc extinguished, where you're just a few inches in a SF6. I mean, it's just not much movement at all. So it's really the newer stuff definitely is more reliable, but I do not agree. And you hear the term maintenance free thrown around a bit these days. I disagree with that completely. I've seen maintenance free fail. So that's you still need to be on your game and you know doing your due diligence to make sure these things are operating properly.
All right. Here's another question. How relevant is the tangent delta capacitance test as a diagnostic test?
On a SF6,
Yeah.
Doble people will hate me. It's not. For SF6, I've looked at enough of them on SF6. I would say I can tell you if it's hot or cold outside when they tested it, looking at the test results, but I can't tell you if the breaker's good bad. And if you think about the nature of it, I mean, SF6 bushing. No, I mean, you know, we don't have capacitive layers there. We have a conductor through a gas insulation to ceramic. That's what we have. So, I mean, it's not, you're measuring more of, it's a bigger measure of temperature and humidity and that type of thing than I've seen them in the wintertime or summertime that look like they were at 5%, and in the wintertime it might be at 0.2. I mean, so it's just kind of with that. Now, if you get into oil breakers where you've got capacity, you know, the oil impregnated bushings, you've got the oil field tank, which also is a type of capacitor we're looking at there. Now, those are something you definitely need to test to understand the health of it. But with the SF6 stuff, I don't see where it has a lot of. I haven't found much usefulness out of it.
Okay. Okay, great. Thanks. Thanks for the presentation. Thanks for those questions.